Hello everyone, in this video I'll be talking about UV visible spectroscopy, and previously I have made three or four videos about UV visible spectroscopy in my playlist of spectroscopy on my YouTube channel. And if you are first time watching my video, just to let you know that I have uploaded about 105 videos on my YouTube channel related to different topics of organic chemistry, starting from natural product chemistry, retrosynthesis, spectroscopy, name reactions, as well as about research topics such as how to write a research paper, as well as how to apply for PhD admissions and scholarships, or how to write an effective email to a foreign supervisor. So please have a look at my channel, and if you feel interested and if you feel that it's good to watch it, then don't forget to subscribe it. Thanks. Let's come back to our topic. Today is presentation of UV visible spectra and how we interpret them, and what is the effect of solvent, and what is a chromophore. And later on in this video we will be discussing that what kind of electronic transitions occur in various organic functional groups, how we can determine them. By the way, let me tell you one thing, that I'm following a textbook of spectroscopy written by Pavia and co-authors. So if you don't have this book, then drop your email below in the comment. I'll send you this book in PDF form by email. So I'm taking straight away the notes from that book, and let's start with this one. Okay, let me grab a pen. Okay, I have a pen. So the topic is presentation of spectra of UV visible spectroscopy, the chapter 7 of Pavia 7.5 topic. So the ultraviolet visible spectrum is generally recorded as a plot of absorbance versus wavelength. So if you look at the UV spectrum, you will find at the x-axis we have the wavelength, and at y-axis we have the absorbance, and we write for A for absorbance and lambda for wavelength. So this is how we plot the UV visible spectrum. It is customary to then replot the data with either molar absorptivity or log molar absorptivity plotted on the ordinate, and wavelength plotted on the abscissa. Figure 7.4, the spectrum of benzoic acid is typically of the manner in which spectra are displayed. That is the figure 7.4. and that is the spectrum of benzoic acid, and that is how we interpret them and write the spectrum. So at the x-axis we have wavelength in nanometers, and y-axis we have molar absorptivity. Go back to this one, then figure 7.4, spectrum of benzoic acid is typical spectrum of the manner in which spectra are displayed. However, very few electronic spectra are reproduced in the scientific literature. Most are described by indications of the wavelength maxima and absorptivities of the principal absorption peaks. For benzoic acid, a typical description might be, so the lambda maximum wavelength for benzoic acid is 230 nanometer, and the molar absorptivity is 4.2, and second peak is at 272 and molar absorptivity is 3.1. Third peak is at 282 and molar absorptivity is 2.9. These are the peaks which appear for benzoic acid in the ultraviolet visible spectrum. Here is the spectrum. So as you can see, the wavelength maximum in intensity is 230, but highest wavelength is 282 and second highest is 272. And this is the UV visible spectrum of benzoic acid, and the spectrum is plotted at x-axis for wavelength against absorptions. Next topic is solvents. How solvents affect the UV visible spectrum. The choice of the solvent to be used in ultraviolet spectroscopy is quite important. The first criterion for a good solvent is that it should not absorb ultraviolet radiation in the same region as the substance whose spectrum is determined. That is the first quality of a good solvent, that it should not absorb. For example, if your compound is showing a absorption at 400 nanometer, or even 300 nanometer, then you should not use such a solvent which also absorb at 300 nanometer. Then it will be hard for you to differentiate whether this peak is because of the solvent or whether this peak is because of your compound. Make sure to avoid such solvents which have the absorption in the UV visible spectroscopy. Usually solvents that do not contain conjugated systems are most suitable for this purpose. Any solvent which does not contain double bond, triple bond or benzene ring or does not have any conjugation, then it's good for UV visible spectroscopy. Although they vary regarding the shortest wavelength at which they remain transparent to ultraviolet region. So table 7.1 lists some common ultraviolet spectroscopy solvents and their cutoff points are minimum regions of transparency. Let's have a look at 7.1. So if you are using acetonitrile, then acetonitrile gives peak in the UV visible spectrum at 190 nanometer. If you are using chloroform, then it gives you a peak in UV visible at 240 nanometer. If you are using cyclohexane, it will give you a peak at 195. If you are using 1,4-dioxane, it will give you a peak at 215. And if you are using 95 ethanol, then you will observe a peak 205. For N-hexane, it's 201. For methanol, it's 205. For isooctane, it's 190. And water is the most suitable because its cutoff point is 190. So most of the chromophores absorb above 190 in the UV visible spectroscopy. So of the solvents listed in table 7.1, water 95% ethanol and hexane are most commonly used. Each is transparent in the regions of ultraviolet spectrum in which interesting absorption peaks from sample molecules are likely to occur. A second criterion for a good solvent is its effect on the fine structure of an absorption band. That is the second important quality of a solvent. Figure 7.5 illustrates the effect of polar and non-polar solvents. So as you know that solvents could be polar and solvents could be non-polar on absorption band. A non-polar solvent does not hydrogen bond with the solute, and the spectrum of the solute closely approximates the spectrum that would be produced in the gaseous state, in which fine structure is often observed. In a polar solvent, the hydrogen bonding forms a solute-solvent complex and the fine structure may disappear. So it's always better to use non-polar solvents. So we discussed this in table 7.1 where we defined the solvent cutoff points for different solvents. Here is the figure 7.5 and this shows you the ethanol and isooctane. These are the two solvents. Ultraviolet spectrum of phenol. This is the spectrum of phenol in ethanol solvent and in isooctane. Now isooctane is very non-polar solvent and ethanol is very polar solvent. Ethanol is capable of making hydrogen bonds with the phenol. Whereas isooctane is a non-polar solvent, it is not able to form hydrogen bonding network with phenol. Now the dotted line spectrum, this one, is taken in ethanol for phenol, and the solid line spectrum is taken in isooctane solvent for phenol. So both of these spectra belong to the molecule phenol, but they are recorded in different solvents. Now if you look at the fine structure of absorption band in case of ethanol, you can see there is a loss of information or loss of peak shape due to the solute-solvent complex formation in ethanol with phenol. As you know that phenol has this sort of structure. It has a benzene ring and an OH group. So this is the OH group that is present in phenol, and this is the OH group that is present in ethanol. So they can make a hydrogen bonding network. So this is CH2 and CH3. So this is CH3 and the CH2 and OH group. Now it is clearly observed, or it is clearly be seen here, that ethanol, which has OH functionality, is capable of making hydrogen bonding network with phenol, and hence due to this, fine structure of the absorption band of the spectrum is lost, whereas the fine structure of absorption band is preserved, and it can be clearly seen in the isooctane solvent. Once again, to mention that on the y-axis we have the absorbance, and on the x-axis we have the wavelength in nanometer. So this is how UV visible spectrum is plotted, and this spectrum is from 220 to 300 nanometer. That is a huge effect of solvents. So solvents play a crucial role in UV visible spectroscopy. Here is more interesting analysis about solvents. So solvents shift on the N to pi star transition of acetone. Lambda max in water is 264. Lambda max in methanol is 270. Lambda max in ethanol is 272. Lambda max in chloroform is 277, and lambda max in hexane is 279. Now you can see that N to pi star transition in hexane is maximum 279, and N to pi star transition is minimum in water, that is 264. One thing can be deduced from this information, that N to pi star transition is greatly influenced by the polarity of the solvents. If we have a non-polar solvent, then we will observe a bathochromic shift. A spectrum will shift towards the higher wavelength, red shift we can say. But if we use a polar solvent such as water, then the spectrum shifts towards the lower wavelength. We call it a blue shift. So that is the essence, or that is the information that can be taken from the spectrum, or from this table 7.2. So what does, again I'm repeating, what does this table 7.2 shows? It shows the information of the N to pi star transition for acetone molecule. So the UV visible spectrum of acetone was recorded in 5 different solvents: water, methanol, ethanol, chloroform, and hexane. Now water, methanol, and ethanol, they are all polar. Chloroform is also polar, but chloroform is less polar than water, methanol, and ethanol. But among all of these solvents, the least polar or most non-polar solvent in the table is hexane. Hence the wavelength is maximum for N to pi star transition of acetone in hexane. A third criterion for a good solvent is its ability to influence the wavelength of ultraviolet light that will be absorbed via stabilization of either the ground or excited state. Polar solvents do not form hydrogen bonds as readily with the excited states of polar molecules as with the ground states, and these polar solvents increase the energy of electronic transitions in the molecules. Polar solvents shifts the N to pi star type of to shorter wavelength. That is the reason we are observing peak for acetone molecule in water at 264.5, and for hexane we observe the peak at 279 for acetone molecule for the N to pi star transition. Why? Because polar solvents, they form hydrogen bonds not with the excited state of the polar molecules but with the ground states of the polar molecules, and these polar solvents increase the energy of electronic transitions. As the energy increases, the wavelength decreases. That is the relationship of energy and wavelength with each other. So energy and wavelength are inversely related to each other. If energy increases, then wavelength decreases. So what does the polar solvent do is they increase the energy of electronic transitions in the molecule at the ground level, not at the excited level. So polar solvents shift transitions of the N to pi star type to the shorter wavelength. On the other hand, in some cases, the excited states may form stronger hydrogen bonds than the corresponding ground states. In such a case, a polar solvent shifts an absorption to longer wavelength since the energy of the electronic transition is decreased. So polar solvents shift transitions of the pi to pi star to longer wavelength. So that is the information that can be taken, that polar solvents, I am writing as PS, they increase the wavelength for pi to pi star transition, pi to pi star transition. They increase the wavelength of pi to pi star transition, and they decrease the wavelength of N to pi star transition. So that is the key point that can be deduced from this topic, or from these lines, that if you are using a polar solvent, what does polar solvent is going to do in your molecule? It is going to decrease the N to pi star transition wavelength, and it is going to increase the wavelength of the pi to pi star transition. So table 7.2 illustrates the effects of a series of solvents on electronic transition that we discussed. Now next topic is what is a chromophore. That will be our next topic, and I'll be discussing in the next video, I think. Yeah, I'll be discussing the chromophore in the next video, and thank you for watching this short video about the effect of solvents on the N to pi star and to pi star transitions in the UV visible spectroscopy. If you have any questions, please feel free to comment below in this video. I'll try to get back to you, and thanks for listening. Take care. Bye.